we're looking at the acid-base theories. First one we're looking at is the one that is proposed by Arrhenius. In 1987, a Swedish chemist by the name of Svante Arrhenius formulated his acid-base theory. For this theory to be understood, it's first important for us to understand how electrolytes conduct electricity, as this concept was the basis on which Arrhenius formulated his theory of acids and bases. He investigated the abilities of aqueous solutions of various ionic compounds and aqueous solutions of acids and bases to conduct electricity using a conductometer. He called these types of solutions that conduct electricity electrolytes. So here we have a little depiction of a conductometer. Essentially what it has is this. It has a power source and two electrodes, okay, connected to the power source by, of course, these wires here. And you have a light bulb here which will light up or not, depending on whether or not something conducts electricity. This is called the anode and that is called the cathode. Now, as it stands here, this is an open circuit. If you want to test the conductivity of any substance, whether they conduct electricity or not, what we do is this. We bridge this gap here. If the substance conducts electricity, this bulb will light up here. And in this case, because copper is a metal, it does conduct electricity like all other metals do, and therefore this light bulb will light up there. What is happening here is this. There exists a potential difference between the cathode and the anode. So when a metal or any other substance that conducts electricity is placed there, because of that difference in electrical potential, the electrons move from the cathode into the anode and the circuit is now complete. The electrons, of course, will pass through here in a continuous basis right away around the circuit like that. And because of that, the filament of this incandescent bulb then to get hot and it glows. So this is how metals conduct electricity. Any other substance's ability to conduct electricity can be tested. So let's say you have a piece of plastic here. Nothing will happen because these do not have free mobile electrons, okay? Metals have that. Now you can also check other substances. If once with the water conducts electricity, I put water there, okay? You see that the light bulb will not light up. Let's say now we want to see if salt conducts electricity there. So solid sodium chloride or any salt would not conduct electricity. But now if I take salt water does conduct electricity. And this is called an electrolyte. Okay? Any aqueous solution that conducts electricity is called an electrolyte. Our job now is for us to understand how aqueous solutions of ionic compounds conduct electricity, and then we'll be able to appreciate Arrhenius' theory of acids and bases. Oh, let me do that too. If I put now solutions of acids and bases there too, same thing, they do conduct electricity, like salt solutions. Bases go there, they also conduct electricity like aqueous solutions of other ionic compounds. So let us see how aqueous solutions of ionic compounds conduct electricity. Then we talk about conductivity in acids and bases. So this is the definition for an electrolyte. We've spoken to that already. An electrolyte is any substance that conducts electricity in its aqueous form, liquid, or in its molten state. Molten means that you heat it until it melts. So if you have some sodium chloride, remember that sodium chloride couldn't conduct electricity in a solid state there just now. If you heat that to the extent that it melts, and then you put those two electrodes inside, you will start see the light bulb is going to glow. Okay? So that means in its molten state, as well as its aqueous form, it will conduct, and therefore that's called an electrolyte. How does it conduct electricity? For electrolyte to conduct electricity, okay? Just like how we said, for this guy to conduct electricity, it must allow electrons to move in this direction. The same thing must happen also for an electrolyte to conduct electricity. Whether you put a base or a solution of a salt, it also must allow the electrons to flow in that direction there. But how does it happen in an electrolyte? We can understand how it happens in a piece of metal because the metals have electrons in them, right? So that's the next job for us to do, is to understand how the electrolyte conducts electricity. Let us say we have some copper 2 chloride solid, some crystals there, and we dissolve that in water. When we dissolve this in water, it dissociates into two ions. It dissociates into copper 2 ions and chloride ions. This is what happens when any ionic compound dissolves in water. We will use copper 2 chloride solution to exemplify how other aqueous salt solutions conduct electricity. When the electrodes of a conductometer are placed in this aqueous solution, this is what is going to happen here. I'm going to show you this figure here. So this is the apparatus here. This is my anode here. And this over here is my cathode, okay? So look what is happening here. We have two types of ions in solution. We have copper 2 ions and we have chloride ions. Because of the positive nature of the anode, the negatively charged chloride ions will migrate towards it due to electrostatic force of attraction between this anode here and these ions here, unlike charges attract. And due to the negative nature of the cathode now, these positively charged copper 2 ions will move towards that. They'll be attracted there. Two important things will happen now. Observe also how I'm showing you here that there is an evolution of chlorine gas at this electrode here on the anode, and there's a deposition of copper atoms on this cathode here. Note those things. So 4 things. Positive ions are going towards that side. Negative ions are going toward that side. Chlorine gas is produced here, and a brown deposit of copper is formed on this electrode here. Let's explain why that is happening. Watch that. At the anode, which is the positive electrode, these chloride ions that go there are called anions. They're called anions because they're going towards the anode, okay? These guys here are called cations because they're being attracted to the cathode or going towards the cathode there. But at the anode side of the conductometer, chloride ions are giving up the electron to the positively charged anode. See, these are 2 electrons there. They'll go on to the anode because the anode is positively charged. They would love to have those 2 electrons. Clear? But in so doing, chloride becomes neutral atoms. And of course, they don't like to stay as atoms. They form molecules. On the other side, though, every Cu2+ ion accepts 2 electrons from the cathode that is negatively charged. So this is full of electrons here, right? Lots of electrons. So these guys go there, okay? And they collect 2 electrons. And that's why copper becomes solid and it deposits itself on the cathode there. So let's go back and watch this figure. The chloride ions are becoming molecules there because they're giving up all the electrons, and you're going to get chlorine gas bubbling through the solution here. You can, if you carry out the experiment, you can actually smell the chlorine gas. If you have damp blue litmus paper here, this is a good nice test of chlorine. Chlorine is acidic. After it reacts with the water and the litmus paper, the blue one, and it will bleach it. Over here now, because millions and trillions of copper ions are deposited here, you get a coating of copper happening here. This is going to continue for a long time because you have lots of ions inside here when you just dissolve a little bit of copper chloride inside there. So it will go on until all these ions here, of course, get depleted. So this is how an electrolyte conducts electricity. See? One set of ions are going there and giving electrons to that, okay? And another set of ions are taking off electrons from that. So via these ions inside here, an aqueous solution of an ionic compound conducts electricity. Okay. So this is how it happens, okay? You can read that there. I'm giving you to read that there, okay? You can make your notes. You can follow my discussion there. And this is what happened. Now listen to this now. Arrhenius observed that if he used aqueous solutions of acids and bases, they also conduct electricity. So Arrhenius is now saying that since it is the ions inside this electrolytes that are responsible for conduction of electricity, he concluded that for acids and bases to conduct electricity, they must have produced ions when they dissolve in water. So when you look at the formulas of acids and bases, every acid is having a hydrogen there. His theory is that when an acid is dissolved in water, it is going to ionize to produce hydrogen. Same thing here. So you have sodium and OH ions, and this conducts electricity. How do we get the ions? Must be this guy that's ionizing there and is producing the hydroxyl ion there, and all of these having hydroxyl ion here. So that formed his basis for his theory. Okay? This is his theory. He's saying that acids produce H plus ions in their aqueous solution. And using this as an example here, hydrochloric acid, aqueous, when you dissolve that, it gives you hydrogen ions. Okay? And that is what causes acidity. According to him, this is what causes acidity. And again, for the base, he said they dissolve in water and they produce OH ions that make them basic. So that is his theory, that when an acid dissolves in water, it produces hydrogen ions. Therefore, an acid is something that produces hydrogen ions, and a base is something that produces OH ions. A few shortcomings for this theory are outlined as follows. Empirical evidence show that acidic solutions contain primarily hydronium ions rather than H plus ions. Of course, we talk about this when we did bonding. We said that these guys don't stay by themselves. They will team up with water molecules to form the hydronium ion. Empirical evidence also shows that aqueous solutions of some salts have pH that is higher and lower than 7, indicating that they're either acids or bases. So if you look at calcium oxide, for example, it doesn't have any H plus or OH inside, yet it has a pH of 10 that indicates it is a basic solution. Sodium carbonate solution doesn't have any OH ion inside, yet it has a pH of 9. And ammonium chloride now, you don't see any free hydrogen there, and it seems to be acidic. So that is the Arrhenius theory. So we'll now look at another theory that was made in 1923 by this Danish scientist Johannes Bronsted and English scientist Thomas Lowry. Okay, we call that the Lowry-Bronsted theory or Bronsted-Lowry theory. Their theory says that an acid is a proton donor and a base is a proton acceptor. This one is similar to the Arrhenius theory. Watch this. What is a proton? If I have a hydrogen atom, it is made up of one electron and a proton. If we knock this electron off as we do here, what is left is what we call a hydrogen ion. But in effect, it is really a proton. So a hydrogen ion is a proton. If you have acetic acid or ethanoic acid in water, this is the theory. According to the Lowry-Bronsted theory, the acid here, which is ethanoic acid or vinegar acid, will donate a proton to water. So because this is donated a proton, it is called acid, and we call it acid 1 for now, okay? Because the water now is accepting that proton, based on their theory, this we call a base. So in this forward reaction here, ethanoic acid is the acid, and because water is accepting the proton, it is called a base. This is the space-filling marker here of the acid. So this will be lost. When that is lost, this is what is left. When this guy gains the hydrogen, this one here, you can see has no extra hydrogen here. So this is what is formed. When this picks up the proton, it forms this. When this loses this hydrogen, it gives you this. But now watch. In the reverse reaction, if this reaction were to be reversed, What will happen now to get back these species here, this hydronium ion will now have to donate the proton to this ethanoic ion. So this now is acting as the acid, and this one here is acting as the base. So you can see how these things change up there. So, of course, water, water had a lone pair here and a lone pair there. One of the lone pairs used in making this hydronium ion here when we talk about coordinate covalent bond there, okay? One lone pair is left there. Okay, why are we putting these ones and twos there? There's something that's called conjugate acid-base pair. When something is acting as an acid, what's left of it is called its conjugate base. So look for two species that resemble each other very closely. You can see this one here resembles that one there, okay? This is the acid, and that is the base. They will call this guy here acid, and this is a conjugate base here. This is a conjugate acid-base pair. What do you see here now? These two resemble each other mostly, right? Very closely. And this one, because this one is acting as the acid here, this must be its base here. That basically is the Lowry-Bronsted theory of acids and bases. For the Ford reaction, you can see in this case, acetic acid is the acid, water is the base. For the reverse reaction now, you see that hydronium ion here is the acid, and this is the base. You can see the resemblance here with the acid and the base here. These are called conjugate acid-base pairs. Watch this here. Conjugate acid-base pair formation. We've spoken about that already. So this is acetic acid. When it gives off the proton there, what is formed is its conjugate base. When hydronium ion loses the proton, what's left of it is its water, which is called the conjugate base. And these are the pairs there. Can we identify any here? Let's see if we do one. You got this. You're asked to do this one. Which one will be the acid here? Obviously the guy with the hydrogen, right? So that is going to go into that guy here. A third theory for acids and bases has been proposed by G.N. Lewis, the same scientist that used dots to represent electrons. The reaction between sodium oxide, a basic oxide, and sulfur trioxide and acidic oxide to form sodium sulfate, a neutral salt, will be used to establish our understanding of this theory. The reaction above is an example of a neutralization reaction, but it does not conform to either the Arrhenius or Lowry-Bronsted theories of acids and bases. G.N. Lewis has broadened the theories of acids and bases to include wounds like that above, where pairs of electrons are transferred from one species to another. A Lewis acid is defined as a species which can form a covalent bond by accepting a pair of electrons from another species. A Lewis base is defined as a species which can form a covalent bond by donating a pair of electrons to another species. Regarding the reaction above, it is the oxide ion that is really reacting with the sulfur trioxide molecule to form a sulfate radical. And this figure here is used to illustrate how that happens. Recall that sodium oxide is formed by an oxygen atom receiving 2 electrons, one from each of 2 sodium atoms. Thus, it acquires an octet with 2 negative charges, as seen here. So in this illustration, the oxide ion is donating an electron pair to the sulfur trioxide molecule to form a covalent bond. The oxide ion is acting as a Lewis base, while the sulfur trioxide molecule, which is accepting the electron pair, is acting as a Lewis acid. As can be seen, this pair of electrons from the oxide ion gets transferred to the sulfur atom in the sulfur trioxide molecule to form a covalent bond between oxygen and sulfur, as identified here. So the one that is accepting becomes the acid. Remember, accept acid. That's one of the strategies that can be used to know which species is the acid or the base. Remember, A is accepting and A is the acid. At the same time, while the sulfur atom in the molecule is accepting the two electrons from the oxide ion here, a pair of electrons from this SO double bond is removed and transferred to this peripheral oxygen atom. And you can see that that pair of electrons that get transferred is identified here. So in the end, you have a sulfate radical with the two negative charges. So this is how the Lewis theory of acids and bases is established. The species that donates a pair of electrons to form a covalent bond is called a base, and the one that accepts the electron is called the Lewis acid. Another example in which the concept of Lewis acid is exemplified is the reaction between boron trifluoride and ammonia. That is a Lewis dot structure for boron trifluoride, and this is what it is for ammonia. The element boron in the compound boron trifluoride is said to be electron deficient, and as such will react vigorously with any species that have electrons to form a covalent bond with. It finds a willing partner in ammonia which has a lone pair. So going back to these figures here, this is the bond here that is electron deficient. Recall that it has a trigonal planar molecular geometry, and the boron atom undergoes sp2 type of hybridization. The ammonia molecule has a trigonal pyramidal geometry, and the nitrogen atom is sp3 hybridized. In this case, it is a nitrogen atom in the ammonia molecule that is donating the electron pair to the boron atom in the boron trifluoride molecule. So the boron trifluoride molecule, since it is accepting the pair of electrons, is called the Lewis acid, and the ammonia molecule that is donating the pair of electrons is called the Lewis base. And you can see that the pair of electrons that is donated here is used to form a covalent bond. Note that when a covalent bond is formed between boron and nitrogen, boron undergoes sp3 type of hybridization. So if one were to look at the shape of the molecule now, if we include the nitrogen with the 3 hydrogen, then this shape becomes tetrahedral. If you do it for the same thing for nitrogen, it'll also be tetrahedral arrangement because now that bond here takes the place of that lone pair. Okay, that's a side point to note. I hope these 2 examples suffice to give you a good understanding of the Lewis theory of acids and bases.